Alright, so let's do a problem now that's one-dimensional and transient. So here's the problem. It's a semi-infinite body. Okay, so here's the surface. The surface is exposed to convection. Right? Initially, all the material is at some initial temperature that's uniform, and because it's a semi-infinite body, we're assuming that the material goes on for forever, which obviously is an approximation that only holds for, depending on how thick the material is, some period of time, but it's a pretty good approximation for short time problems. The surface of the object is exposed to fluid via convection, and the fluid temperature initially at time equals 0 is the same as the material temperature, but then you can see that the fluid temperature begins to rise linearly with time, right? So you have this ramped fluid temperature. And we'd like to know what the temperature distribution is inside of here, what the heat transfer is from the fluid to the wall, and maybe also what the surface temperature is. So we can solve this using Laplace transforms. We can solve this using a numerical model. We can actually get a pretty good idea of what's going to happen without doing any kind of sophisticated analytical or numerical model. If we just sort of use our concepts of how thermal waves behave as they move through material, so conduction waves or diffusion waves, whatever you want to call them. And that's probably a good thing to do before we begin the process of actually solving it, so that when we get done and we have a solution, we can look at it and make sure that it matches our physical intuition. So if you think about what's going on here, heat is being transferred from the fluid out here to the material in here that's still cold, right? And that energy transfer process has to go through two resistances, right? The first resistance is this convection resistance that sits between the fluid and the surface. And then the second resistance is a conduction resistance that goes between the surface and the material that sits way out here that is still unaffected by the surface disturbance, right? So there's a conduction resistance associated with this material that lies in the thermally affected zone, if you want to think about it. And that conduction resistance must be growing all the time because the thermal wave is getting bigger all the time. So our conduction resistance is kind of interesting. It's the distance we have to conduct, which is some fraction of delta sub t, so we'll put delta sub t here. It's the thermal penetration distance here, right? It's growing all the time, divided by k times AC. So what I really have is a resistance network where one of these two resistances, the convection resistance, never changes, but the conduction resistance grows all the time, right? This delta sub t is proportional to the square root of alpha times time, right? So it's growing like the square root of time. This temperature here is increasing linearly, and this temperature here on the other side of my resistance network is just fixed at T initial, right? Because if I go far enough out into the material, I'm always going to find material that doesn't know anything has happened yet. It's going to be at T initial. So this is our not exact, but very approximate, but very useful model of what's going on, right? So we can learn about the process without doing a whole lot of math, just by using this very conceptual model. So let's start with what is Q dot. So Q dot is, it's going to be this temperature minus this temperature, so T infinity minus T initial, divided by the sum of these two resistances that are in parallel. So T infinity is growing linearly, so it's T initial plus beta T, so minus T initial gives me just beta T. This is my temperature difference between the material's initial temperature and the fluid temperature, right? My temperature difference is growing linearly. And then I have R convection, which is this fixed value, and R conduction, which is this increasing value with time, right? So there's my very approximate model for how the heat transfer should behave. And actually, if you look at this for a second, what you can see is it varies with time in kind of an interesting way, right? You can kind of divide time up into two regimes. There's an initial regime where time is small, which means then that if you look at this, this resistance is going to be a lot smaller than this resistance, right? That's my sort of small time behavior. And then there's a larger time regime where this resistance has grown such that it's much bigger than this resistance, right? So there's this long time regime, and they're very different from one another, right? And so you go from a small time regime to some period of time where both resistances are important to finally a period of time where only the conduction resistance is important. All right, so if you think about that, then in the small time regime, this resistance basically goes away, and I'm left only with this resistance. So that gives me this equation right here, and it says that the heat transfer rate is increasing with time proportional to time to the first power. All right. Does that make sense? Well, let's see. The temperature difference is increasing like time to the first power, and at least initially you can see that the only resistance that's important is a fixed resistance. So yeah, the heat transfer rate should go like time to the first power. And then if you wait a long enough period of time, this resistor is not very important. I'm left only with this resistor. So I get this equation right here. And if you look at that for a second, let's see, time to the first power divided by the square root of time. This says that if I wait long enough, the heat transfer rate is going to continue to grow, but now it's only going to grow like time to the 0.5 power, so like the square root of time. So does that make sense? Let's see. My temperature difference continues to increase like time, right? But the resistance that's important, this conduction resistance, is increasing like the square root of time, right? So yeah, my heat transfer rate doesn't increase as quickly as time goes on. If I'm interested in the surface temperature right here, so the surface temperature is the surface temperature is going to be T initial. So it's going to be this temperature here, plus the temperature rise across this resistance. So it's going to be Q dot times R conduction, right? You could do it the other way and say it's going to be this temperature minus the temperature drop across this resistance. But let's do it this first way. It's going to be T initial plus R conduction times Q dot. Okay. So again, I'm going to have sort of two regimes. I'm going to have this initial regime where this resistance is not very important, and this resistance is very important. So we said that in that regime, here's my Q dot, so I can plug that into here. And then our conduction is the same in both regimes. It doesn't matter. It's always 2 times the square root of alpha T divided by KAC. So in the small time regime, my temperature elevation at the surface is going to be what? It's going to be R conduction multiplied by Q dot. And that's going to give me something that's growing very quickly, actually. It's temperature, it's time to the 1.5 power. So initially I should see that surface temperature rise very quickly, right? Like temperature to the 1.5 power. And the reason is because the heat transfer rate's increasing like temperature, and then my conduction resistance is increasing like temperature to the 1/2 power, right? So 1 plus 0.5 is 1.5. And then at long time solutions, if I wait long enough, I should find that this should actually be the other way. I'm sorry. This should be like this. That this resistance, this conduction resistance, is much bigger than the convection resistance, and so I get this slower increase in my heat transfer rate. So this is Q dot is like time to the 0.5 power. So if I multiply 0.5 and then by 0.5, I get that eventually the temperature rise is going to be just proportional to time, right? Actually, if you look at this for a second, you can see that this cancels with all of this stuff, and you're just left with beta times time, right? So the surface temperature is going exactly like the fluid temperature. Does that make sense? So if I wait long enough, what's happening? This resistance is important, and this resistance is unimportant. So if I wait long enough, what's happening is my surface temperature is becoming really, really close to the ambient temperature, right? So eventually the ambient temperature is sort of just impressing itself on the surface, and I get beta times time. So when I look eventually at my solution, I ought to see this kind of behavior, right? If I look at the heat transfer rate, I should see initially that the heat transfer rate increases like time. So this is on a log plot, you know, a slope of 1. Every decade over here gives me a decade here. But if I wait long enough, I should see that it's only increasing like time to the 1/2. So now every decade here should only give me half a decade here, right? So that would be something to look for. If I'm looking at the surface temperature rise, so this is Ts minus T initial, I should see initially that every decade of time gives me 1.5 decades of surface temperature rise. So I should see this initial, you know, small time regime, and then eventually I should see this linear regime where a decade of time gives me exactly a decade of surface temperature rise. Right? So that's some behavior that I expect that I could anticipate without ever having to actually solve the problem. Right? The other question you might ask is, you know, what is this characteristic time? When do I stop going from a short time regime and start going to a long time regime? And of course the answer is it's not a sudden transition, right? You're going to go from a period of time where this is important and this is completely unimportant to one where both are kind of important to one where eventually this one's important and this one's unimportant. So if I want to know what the transition is between those two regimes, the easiest way to do that is to say, well, when are they both equal to each other, right? That's exactly when one stops being dominant over the other. And if I set those two things equal, I can come up with this characteristic time, right? This characteristic time of when I'm going to transition from small time to long time regime. So the way to think about this is if time is, let's say, 10 times smaller than this value, I would be clearly in a very small time regime. If time is 10 times greater than this value, I'm in a long time regime. It's only when time is within an order of magnitude of this value that both resistances are important. All right, so when we're done, we will look at the solution sort of with this in mind and make sure that you know, we're seeing the behaviors that we sort of anticipated. But let's go ahead and try to solve this problem exactly. So I'm going to derive the governing differential equation. We've done this enough times that if you're unsure of any of the steps, you can see them here. But in the end, you get this governing differential equation right here, right? So it is a partial differential equation, right? Temperature is a function of both position and time. It's the same partial differential equation we solved for separation of variables. I need, let's see, it's first order in time. So I need one boundary condition, and that is that at time equals 0, the temperature at all x positions is T initial, right? So this is my initial condition. And then I need two boundary conditions in x because it's second order in x. So my computational domain goes from 0 to infinity, right? So I need a boundary condition at 0, and then I need a boundary condition at infinity. And the boundary condition at infinity is basically enforcing the idea that this is a semi-infinite body. So if I go far enough out into the material, I'm always guaranteed to find some material that has no idea anything happened at the surface and is still at T initial. So that's my boundary condition at infinity. My boundary condition at 0 is just obtained using an interface energy balance. So if I draw a control surface just on this side of the interface and another one just on this side of the interface, what's going in here is convection. So that is H times T infinity minus T at x equals 0. And then what's leaving the other side in the positive x direction is conduction. So that's my, my second boundary condition. So here's my math problem. And we're going to try to solve this guy using Laplace transforms. So we said that there's 3 steps to Laplace transform. The first step is you take your problem and you transform it to the S domain. Hopefully it becomes easier to solve in the S domain, and then you try to get it back into the time domain. So let's follow these steps. First step is let's take our problem. So here's our problem, and we will transform it to the S domain. So I can do this term by term. So this first term is a partial derivative with respect to x. If I go look at my useful properties of Laplace transform, I see that when I take the partial derivative with respect to x, if I transform that into S domain, it remains a partial derivative with respect to x, right? So now this d squared t dx squared becomes d squared t hat dx squared, right? And it's important you keep in your mind that this was a function of x and time. This is my temperature. This is my Laplace transform temperature. It's a function of x and s. Okay, this is my partial derivative with respect to time, so I use this property right here, and it says that then I'm going to get 1 over alpha, so here's my constant, times s times t hat, so my partial derivative went away, and minus the temperature at time equals 0, which for this problem is T initial. So I just plug this into here and this into here, and I get this equation right here. Right? I'm not sure why I felt the need to put it here twice, but there it is. Right? That's my math problem that we need to solve. So this is, as promised, easier to solve in the S domain than it was in the X domain. Right? This is just an ODE in the X domain. Right? I don't have any derivatives with respect to time. I only have derivatives with respect to X. So if I just rearrange this to make it look a little more familiar, here's my ODE. Right? It's second order. It's not homogeneous. I know how to solve ODEs like this. I split them into a homogeneous ODE, which I did here, and a particular ODE, which I did here. My homogeneous ODE, we've talked about this form of an ODE before. There's a minus sign here, so this is going to be solved by either sinh and cosh, or I could also use exponential with a positive argument and a negative argument, right? It's up to you which you use. One choice is going to be clearly easier than the other choice, right? So when we were doing separation of variables problems and we had a bounded computational domain, we chose sinh and cosh, and that was a handy way to go, because usually we're evaluating a boundary condition at x equals 0, and one of these two would go away, right? When you have an unbounded domain where x is going to go to infinity, it's almost always easier to use exponentials. And the reason is because as x goes to infinity, one of these is going to go to 0, and the other is going to go to infinity. So one of these two is going to go away. Whereas sinh of infinity and cosh of infinity are difficult to deal with if you're not clever. So this is the way to go right here. So we'll use this for our homogeneous solution. So let's go up here and look at our particular solution. So if I think about using the method of undetermined coefficients, my right side, the non-homogeneous term here, is just a constant. So that suggests to me that my particular solution should just be a constant. If I plug that constant up here into this and I take two derivatives of the constant, I get 0. Here's my solution that determines that constant. So my constant, my particular solution, is just T initial divided by S. So my solution in the S domain is right here. It's it has two undetermined constants, C1 and C2. But this solution right here will solve this differential equation right here no matter what value of C1 and C2 I choose, right? So it's a general solution. So how do I pick C1 and C2? Well, I have to use boundary conditions. But my boundary conditions I left behind in the time domain, right? So the next thing I got to do is transform these boundary conditions into the S domain and use them.